Good morning, advisors, and thanks for attending my presentation for my dissertation prospectus. The topic of my dissertation is Optimization of Groundwater Long-Term Monitoring Network with Ant Colony Optimization. This is an outline of the 6 topics that I will cover in my dissertation. However, in today's presentation, I will only be covering the first 3 chapters. Those include the Introduction to Long-Term Monitoring Network, Introduction to Ant Colony Optimization, and the variant ACO developed in this study. Let's begin with an introduction to Long-Term Monitoring Network, Chapter 1. Let's start from some background knowledge. Question 1. Why is groundwater monitoring network necessary? We all know groundwater is the water stored in underground spaces like natural cracks, caves, channels, or spaces between soil particles. And groundwater is a primary source of our drinking water and also provides water for agricultural irrigation and in some industry practices. In rural areas of Florida, 96% of drinking water comes from groundwater. Unfortunately, groundwater, especially aquifers, and especially shallow aquifers that have a permeable water table, such as the aquifers in Florida, are susceptible to pollution in many ways and from many sources, both natural and human-induced, such as naturally occurring chemicals leached from soil or rocks by percolating water dissolved in groundwater, gasoline and oil spilled on roads, or leaked from underground storage tanks, road salts, septic tanks, agricultural activities, and landfill leachate. Therefore, monitoring changes in groundwater quality and quantity with groundwater monitoring networks is an indispensable practice for groundwater management agencies in the phases before contamination is reported, during contamination remediation, and after remediation is completed. Now we move on to the second question. What is groundwater long-term monitoring network? Well, groundwater long-term monitoring network deals particularly with groundwater monitoring in the phase when remediation process is already terminated to 1. Validate the conclusions of a remedial investigation / feasibility study. 2. Determine if contamination is mitigating off-site or off-base. 3. To determine if contamination will reach a receptor, such as a drinking water well supply well. 4. Track contaminants exceeding some standards. 5. Track the changes in shape, size, or position of a contaminated plume. 6. Assess the performance of a remedial system, including monitoring natural attenuation. 7. Assess the practicability of achieving complete remediation. 8. Satisfy regulatory requirements. The lifespan of LTM network is approximately 30 years. Next, why optimize and how to optimize LTM networks? Well, let's see the primary problem with most LTM networks. LTM networks generally evolve from groundwater monitoring networks managed for contaminant remediation. To obtain sufficient data for remediation purposes, plenty of monitoring wells are installed and sampled with high frequency. In the long-term monitoring phase, the extent of contamination diminishes. Monitored parameters become more predictable. It may be feasible to reduce the monitoring frequency, locations, and analytical requirements while meeting monitoring goals and data sufficiency. In the meantime, at large remediation sites, the cost of maintaining and operating an LTM network over a large number of sampling locations with numerous contaminants for frequent monitoring for decades can be a significant, persistent, and growing burden for related environmental management agencies. Removing redundant wells and or reducing sampling frequency while meeting monitoring goals and data sufficiency are suggested to be a feasible solution to reduce the cost of LTM network management. In rare cases, however, when environmental conditions change at certain locations, new wells may be added into existing monitoring networks to improve data accuracy. So, LTM network optimization can be achieved by spatial and or temporal optimization. Reducing spatial and or temporal redundancy is the primary practice for LTM network optimization. Recent popular methods for LTM network optimization include geostatistical methods genetic algorithms and its extension methods, monitoring and remediation optimization systems, and ant colony optimization. This dissertation will focus on reducing spatial redundancy in LTM networks using a variant of ant colony optimization developed in this study with IDW, ordinary crindering, and modified inverse distance weighing as data interpolation methods. MIDW is a development in this study. Next, I will pose two scenarios about reducing LTM spatial redundancy. In the first case scenario, the goal is to minimize the cost of LTM, i.e., to minimize the number of monitoring locations while subject to a constraint on overall data loss. This scenario is presented as minimize n, such as data loss is less than or equal to the threshold, where n is the number of remaining wells. In the second case, a given number of monitoring wells are to be removed from the LTM network. Effort is required to identify the given number of redundant wells so that removing them will cause minimal data loss. That is, minimize data loss such as z is equal to n, where n is the number of remaining wells. The second scenario is the focus of this study. Now we move on to the second chapter of this dissertation, Introduction to Ant Colony Optimization. Chapter 2, Introduction to Ant Colony Optimization, will be presented in the following 6 sections, including what is ant colony optimization, the basic ideas behind ant colony methods, the characteristics of ant colony optimization methods, ant colony optimization initial version and its extensions, the applications of ant colony optimization, and ant colony optimization algorithms. What is ACO? Ant colony optimization methods are a group of the most successful optimization methods of swarm intelligence. The initial versions of ACO is the ant system, known as AS, which was introduced by Dorogo in the early 1990s. To resolve traveling salesperson's problems, ACO was inspired by the foraging behaviors of real ant colonies when searching for food. Ants initially explore the area surrounding their nest in a random manner. While moving, ants deposit a chemical called pheromone on the ground. In the same time, pheromone also evaporates into air. Short paths get more pheromone deposits. The later ants tend to pick paths with stronger pheromone smells and also deposit pheromones on those paths. As a result, more ants are attracted to shorter paths and more pheromone is deposited, which in turn attracts more ants. The short path, which is picked by all the ants at the end, represents the global optimization solution. The ant colonies rely on swarm intelligence and food foraging. Their behaviors have the following characteristics: stigmetric, autocatalytic behavior, and positive feedback. Stigmetric means inside a colony, ants communicate via pheromone to establish the shortest paths between nests and food sources. Autocatalytic behavior means the more the ants follow a trail, the more attractive that trail becomes and attracts more ants to follow. Positive feedback means the probability of discrete path choice increases with the number of times the same path has been chosen. Those are also the characteristics of artificial ants and ACO methods. The initial versions of ACO, the ant system, was found to be inferior to state-of-the-art algorithms for the TSP, as well as other combinational optimization problems. Therefore, several extensions and improvements of the original AS algorithm were introduced over the years. Ant colony system methods, known as ACS, and max-min and system methods, known as MMAS, are believed to be more successful members in the family of ACO algorithms. Other successful variants of ACO include the elitist AS, rank-based AS, and the most recent improvement called Hypercube Framework. Since its development, ACO algorithm has received attention of researchers in various areas. ACO methods have been applied to many combinational optimization problems, such as water resources management, quadratic assignment to protein folding, routing vehicles, random number generators, and autonomous decentralized shop floor routing. Yohani and Dr. Chan Hilton introduced ACO into groundwater LTM network optimization in 2006. This study makes some significant improvements to their work in the ACO algorithm using IDW, MIDW, and OK as data interpolation methods to solve LTM optimization problems. The widely accepted definition of the ACO meta-heuristic covers the basic ACO and most of its extensions for combinational optimization problems. ACO methods improve solutions to CO problems through iterations starting with definition of two sets of variables, one set of which is a finite set of solutions, component C, to assemble solutions to the CO problem. The other set is a pheromone values, which is parameterized probabilistic model. The ACO approach attempts to solve an optimization problem by iterating the following two steps. 1. Candidate solutions are constructed based on the pheromone values on each trail inside function and base solution construction, calculating a parameterized probability distribution over the solution space to find out the temporary solutions for each iteration. 2. Update the pheromone values at the end of each iteration with function pheromone update, using the temporary solutions generated in this iteration in a way that is deemed to bias future sampling towards high quality solutions. ACO is an iterative algorithm with the principal while loop. The pheromone values are updated by the pheromone model at the end of each iteration. During the iteration, the set of pheromone values in previous iterations is used to probabilistically generate solutions to the problem for the next iteration, under consideration by assembling them from the set of solution components. The ACO is implemented with a while loop as following pseudocode. While termination conditions not met do, schedule activities, AMP-based solution construction, pheromone update, end schedule activities, and while. The inside ANT-based solution construction component, artificial ants behave as probabilistic constructive heuristics that assemble solutions as sequences of solution components. Each solution construction starts with an empty sequence vector. Basically, this means that the ant checks whether the unvisited vector is empty or not. If not, the ant picks one city C from the vector N, puts in vector S, so the path will extend from the current point to point C. N drops one city, then the ant checks whether N is empty or not. If N is empty, it ends the loop. If not, it goes back to pick another city from N. Choose C from N, a vector of non-visited cities, and extend S to include C. Then determine whether N is empty. If yes, get out of the loop. If not, continue the loop. The choice of a solution component from N is made at each construction step as implemented in the choose from NS, based on the probability which is calculated with respect to the pheromone values as demonstrated below in equation 1, where N is an optional weighting function which, according to the current sequence, assigns a heuristic value N, or being calculated depending upon the problem to be resolved. The exponents alpha and beta are positive parameters whose values determine the relation between pheromone information and heuristic information.
The choice of a solution component from N is made at each construction steps, as implemented in choose from N based on the probability which is calculated with respect to pheromone values as equation 1, where N is the optional weighing function which, according to current sequence, assigns a heuristic value in CG, were being calculated depending on the problem to be solved. The exponents alpha and beta are positive parameters whose values determine the relation between pheromone information and heuristic information.
The implementation of function pheromone update is accomplished using the following. At the end of each ant foraging iteration, pheromone density at each trail is updated according to the pheromone models, which consist of two parts, pheromone evaporation and pheromone disposition. Pheromone evaporation uniformly decreases the pheromone values along all the paths. Pheromone deposition increases the pheromone density on the paths which are traveled by ants in the former iterations, based on temporary solutions to the CO problem. Pheromone evaporation simulates a form of forgetting, favoring the exploration of new areas in the search space. Pheromone updating can be expressed by the following equation, entitled Equation Number 2 below. S upte denotes the set of solutions that are used for the pheromone update. Beta is the pheromone evaporation rate between 0 and 1. F is the quality function. The goal of the pheromone update is to increase pheromones values associated with good solutions and decrease those that are associated with bad ones. ACO methods have several different variants, such as ant system, ant colony system, max-min ant system, elite, ACO, etc. Those variants differ primarily in the way the pheromone values are updated. Now we will delve into section 3 of this dissertation, the variant ACO developed in this study. The presentation of the variant ACO developed in this study will be presented in 3 sections. The first section, the primary differences between variant ACO and the general ACO, the procedure of using the variable ACO for LTM is for ants to search for the best route. And the third topic is summary of using the variable ACO for LTM to identify the ideal redundant wells. The primary algorithm differences between variable ACO and the general ACO are 1. Introduce a shuffle function to improve the randomness so that all the wells have similar chance to be evaluated. 2. Split trails into sections which are defined by the pair of nodes at two ends. The manipulation of pheromone is actually related to section instead of trails. Solution construction progresses through extending trails by adding sections. 3. The approach the pheromone is updated by is, at the end of each iteration, the study classifies the trails into 3 categories, and pheromone along the trails is updated correspondingly. The 3 categories include 1. Not visited by any ant pheromone on those trails is updated with equation 3 noted below. Category 2 is visited by elite ant in a colony, that is, the ant who identifies the group of redundant wells, removing which results in least data loss. The pheromone on this trail is updated with equation 4, where E is elite factor. Category 3 is visited by any ant. The pheromone on this trail is updated with equation 5, noted below. The procedure of using the variable ACO for LTM is for ants to search for the best route is demonstrated in figure 1. This variable ACO consists of 3 loops. Loop 1 for iterations, loop 2 for any ants in the colony, loop 3 for the number of redundant wells. The procedure of using the variable ACO for LTM is for ants to search for the best route, which is demonstrated in figure 1 below. The variable ACO consists of 3 loops. Loop 1 for iterations, loop 2 for ants in the colony, and loop 3 for the number of redundant wells. Summary of using the variable ACO for LTM to identify the ideal redundant wells. 1. The algorithm starts with a colony of ants, each sitting at an imagined location outside the searching domain. At the beginning of each iteration, the ant colony enters the domain with every ant randomly picking a node, and at the same time, adding the picked node into its route memory. 2. Ants move from current node to the next node, extending path by one node. This action consists of several subtypes. A. Shuffle the order of remaining nodes in the unvisited node list so that all the remaining nodes have equal chance to be visited by the ants. B. Estimate the relative interpolation error at each unvisited well with the data at its neighbor wells using IDW, MIDW, or OK data interpolation. C. Calculate the probabilities of an ant to move from its current well to each of all the unvisited wells. D. Use the probability values obtained in step C and a random number to choose the next well for an ant to move to. E. Extend the path to the newly picked well. Update the flag variable from 0 to 1 for the edge which was traversed by the ant. Step 3. Has the ant identified the given number of redundant wells? If not, repeat step 2. If yes, move on to step 4. In step 4, do all the ants in the colony finish the route identification? If not, repeat step 2 and step 3. If yes, calculate the error, which is the root mean square error, or root mean relative error, for the routes picked by all the ants in the colony, and classify ants into two groups. Best ants, which identify the group of redundant wells with least data loss, and regular ants otherwise. 5. Update pheromone density along all the edges in the domain in the following rules. A. If an edge has not been chosen by an ant, use equation 3 in section 3.1. B. If an edge is on the path of best ant, use equation 4 in section 3.1. And C. For the edges which were passed by regular ants, use equation 5. 6. The best so far route and least data interpolation error are also updated at the end of each iteration by comparing the least so far data error with the least iteration data error. If least so far data error is greater than the least iteration data error, the current least so far data error is updated with the least iteration data error, and the current best route so far is also updated with the best iteration route. Step 7. Is the required iteration finished or converged condition met? If not, repeat steps 1 through 6. If yes, report the best route and wells which are identified by this solution and its resulting least data interpolation error. Job done. So far, the presentation of prospectus is finished, but let's peek into a little bit about chapter 4 and 5 of this thesis. The next chapter, chapter 4, will go over testing the variable ACO with synthetic LTM network. Chapter 4 covers 4 sections. Section 1, generate synthetic LTM network. Section 2, optimizing the synthetic LTM using a enumeration method with IDW and OK as data interpolation methods. Section 3, optimization of the synthetic LTM using the variable ACO method with IDW and OK as data interpolation methods. Section 4, evaluate the performance of variable ACO against enumeration methods. Chapter 4, Part 1, generating a synthetic LTM network. First, a synthetic plume is generated by injecting an unreactive contaminant with a mass m instantaneously into an extensive saturated homogeneous aquifer of the thickness b and average pore velocity of v. The contaminant transportation through advection, and dispersion is governed by equation 6, stated below. Chapter 5 presents the application of variable ACO to site LTM networks. This chapter is organized into 4 sections. Section 1, site description. Section 2, data analysis. Section 3, LTM optimization with variable ACO. And Section 4, results analysis and summary. Section 1, site description. The field data were collected from 30 wells inside an LTM network in the upper aquifer at Fort Lewis Logistics Center within the Fort Lewis Army facility in Pierce County, Washington. The site is underlain by an extremely complex and heterogeneous sequence consisting of sand and gravel glacial deposits. Those diverse deposits are broadly categorized into an upper aquifer and a lower aquifer. Let's stop here. The rest will be presented next month in my dissertation defense. Thanks for listening. Are there any questions and comments? Figure 11 shows the distribution and contaminant concentration contours of the 30 monitoring wells in the logistics center. The numbers are the IDs of the monitoring wells that don't have any physical meaning and do not indicate the order of the wells either. On this figure, the unit of contaminant concentration is wrong. The unit should be measured in milligrams per liter. The error will be corrected soon. The contour shows the source of the TCE contamination is in the southeastern corner. Figure 12 shows the interpolation results of the TCE concentration for 30 samples with IDW, OK, and MIDW. The y-axis represents TCE concentrations and the x-axis represents the IDs of the monitoring wells. There is no physical relationship between those IDs. The lines between the markers do not mean anything. The lines are put in the figure just to differentiate the concentration values interpolated with different geostatic methods. All the dots connected by a same line are the interpolation results using the same method. It is indicated in the figure that in the well with ID 20, the highest concentration of TCE is 0.6 milligrams per liter is detected at some other wells. The TCE concentration is close to 0. The absolute interpolation error is observed at well 20. Relative error of concentration interpolation for the 30 samples is shown in figure 13. Relative estimation error is defined as the difference between real values and interpolated values divided by the smaller one of those two. It is observed that MIDW functions better than IDW and OK at wells where abnormally big differences of GCE concentration from neighboring wells exist. This is related to the definition for MIDW. At wells 12 and 16, the ERR related to IDW and OK is greater than 1,000, significantly larger than the values of most other wells. And the ERR at wells 20 is below 50, although the absolute error at well 20 is the largest in the site. Review of Figure 11 reveals that wells 12 and 16 are close to the source of contamination in physical distance, while the TCE concentration is quite different. The TCE concentration at those two wells cannot be interpolated with acceptable accuracy using the data from neighboring wells, so those two wells are suggested to be kept in the LTM network, and also will not participate in the data interpolation at the remaining 28 wells. This study demonstrates the optimization of the 28 well LTM network using variable ACO with IDW, OK, or MIDW as data interpolation methods individually.